Hi, my name is Stephen Lantz, and I'm doing a 2111 extra credit physics project on a lecture I went to earlier this semester called Patterns in Nature. I'm interested in this topic because I love nature and I love being outside, whether it's camping or fishing or hunting or just being out with my friends in general. I also love learning about patterns. I think they're very interesting, and the Fibonacci sequence is one pattern that we see all throughout nature that we'll be discussing later on in this PowerPoint. Dynamic equilibrium is one aspect of nature that we see all over the world, really. And beach cusps are one example of dynamic equilibrium. Beach cusps are formed by the waves in the ocean through moon activity, lunar activity, and just the way that the water moves up and down the beach starts to form these little cusps in a very distinct pattern that are called beach cusps. It looks almost like a sine wave. It's very interesting. Like I said, we're going to talk about the Fibonacci sequence. The Fibonacci sequence is a pattern where you take a number, and that number is formed by adding the two previous numbers to it, so it's gradually getting bigger and bigger. It's named after Leonardo of Pisa, who was called Fibonacci, around 1200 AD. And you can see the sequence in flowers and seashells and a lot of different places. It's really interesting to look at, and it really makes nature really beautiful too. Another thing that was talked about in the lecture was the fact that nature is self-organized. As you can see in beehives and lightning and sand formations, that nature finds a way of organizing itself, whether it's creatures like bees knowing the most efficient way to create their beehives, or just lightning itself, the electricity forming out and branching out. It's very, very interesting, and as you can see in the sand waves as well, how they form a very distinct pattern. And it's very, very organized as well, and really interesting to look at. Stability in nature is another key topic covered in the lecture, and this also corresponds to the Fibonacci sequence. Other elements we talk about, other patterns we see. One exception to that fact is looking at a windy river, such as like the Amazon or really any other river that winds so intensely. Stability is so important in nature because water in these massive rivers will overflow on the banks and destroy other wildlife if it's not secure within the banks of the river. And so while rivers may not reach their destination the most quick way possible, they are very stable and tend to slow the water down to make sure that water does not move too rapidly and destroy overgrowth on the banks of the river. That's just one example. More examples are just trees in general, the way they grow. Obviously form pretty symmetrical shapes most of the time, not always, but most of the time. And mima mounds, or mima mounds, are another example. It's really hard to describe exactly what mima mounds are. They are found in many parts of America near the Mississippi River, and also further west like California and Oregon. And basically they're these mounds formed in soft sediment ground type areas by really intense seismic activity, and this seismic activity, this shaking, forms these little mounds in a very symmetric and stable manner. The last example on the bottom right is called axial segregation. It's just a graphic displaying that, and basically what's happening here is the particles in this cylinder are segregating themselves into lines while the cylinder is rotating. So eventually you're going to be forming different distinct straight lines. So while you might have particles spread out all throughout the cylinder, they'll eventually separate out to form axial segregation. Another aspect is showing stability of nature. And in conclusion, it's really interesting to talk about this stability in nature and just nature in general, because there's so much to learn. This is only the tip of the iceberg. There's so many aspects of nature and patterns in nature that we see that we can't really explain yet. And so it's really exciting to look into the future to see what we will be looking at 100 years from now, 1,000 years from now, as we're trying to figure out this whole planet that we're living on, and even beyond the planet too. And so it'll be really interesting to see what we can come up with next. Thank you very much for your time. I hope you enjoy the video.